Welcome to a lesson with Dr. Powell. Let's talk about how we can find the adjacency matrix for a digraph. So something with vertices and directed edges between them. So the idea is that we're looking at a function which tells us, given an origin or a collection of origins um, from from that collection, how many paths are there from that collection that hit V1? How many paths from that collection hit V2, V3, and V4? And we're going to say these paths are of particular length, like how many paths of length 1 for an adjacency matrix is just length 1. What does that mean? That means 1 arrow worth. So how many, so for instance, if we start at V, so let's suppose our origin is just simply V1. Then how many paths coming out of V1 hit V3? That would just be 1. How about V2? There would be 2. V4, there would be 1. How about V1 to V1? There's none. So there would be a 0. Now, if you could do a collection of them, like starting from V1 and V4, how many paths of length 1 come from this collection into V2? You could say, well, there's 2 coming in, they both come from V1. From this collection, there's 1 coming to V3, and there's none coming to V1 again. And let's see, from this collection, how many to V4? Actually, notice this. There's 1 coming from the collection to V4. It's within the collection itself. So this idea, how do we make a matrix, describes this process. So to do this, what we're going to do is we're going to think of a row interpretation and see where standard basis vectors go. Our standard basis vectors are going to be the vertices themselves. We're going to say these are just form a basis. They're linearly independent. We're just going to say these objects right here, just going to call them vectors. So we're going to say V1, where's it going to head? Think of a row interpretation. It's, so we think of V1 as being the origin. And let's see, nothing of length 1 comes from this origin, from this V1 and hits V1. So we just say 0 for that. Now, what about V2? It looks like there's 2 paths that come from V1, see, coming from V1 into V2. And then from V1 into V3, there's 1. And then from V1 to V4, there's 1. Okay. So then we see, where does V2 head? All right. So V2 looks like there's 1 path to V4 and no other paths anywhere else of length 1. So it looks we could just fill in like this. All right. What about V3? Well, it looks like V3 has no arrows that come out from except to itself and is 2 going to itself. So we think 2. Now notice the way I've kind of notated this. I'm kind of going in order. I'm kind of thinking, well, out to V1 and out to how many things are hitting V2? How many things are hitting V3? How many things are hitting V4? I've kind of organized this output in the following way. So this, so you can kind of, so we're kind of, what we're doing is we're building a matrix function, if you will, or linear transformation that goes from R4 to R4. R4, the beginning is just collection of tuples of, or collections of vertices, K in here. And then the output in R4 is simply just how many paths to that particular point. Now, notice how I wrote R4, R4. Now, in particular, the way that we're really writing this down, this really should be more like whole numbers to whole numbers. And so integers to integers, but you might even want to think, well, what about, positives and negatives, and how does that work? Well, at least for now, we're going to be, a map like this will restrict, or like this will restrict down to what we want in our particular situation. And so, because our particular situation of paths is actually scalable and additive, and so, I mean, it's additive really, here. in this case. So, which means that a matrix can describe it. Of course, the matrix will describe more than what we want, but that's because we have more things that can go on with real numbers, but that's okay. It still really does a lot of what we need. V4, where would that head? So we see where does notice you have nothing coming out of V4, and so we just have bunches of zeros right here. So this is our adjacency matrix for this particular digraph. Okay. Now, what if we want to think about this adjacency matrix composed with itself? What does that mean? Like, suppose this adjacency matrix is A, and we compose it with, so it's a function, compose it with itself. It's like matrix multiplying, so A squared, like running this twice over. Well, this answers the question for paths of length 1, and naturally, if you compose this question with itself, it's paths of length 2. So you could actually figure out what A squared is either by doing direct matrix multiplication or just by looking at this and thinking about, in turn, what happens with paths of length 2. So we could think, and let's just write it right here. V1, where is that going to be? So paths out of V1 of length 2 that hit everything. Well, again, to itself, there's nothing. To V2, paths of length 2 that hit it well, let's see, these will end up going there, so that doesn't work. Maybe, and then, yeah, it doesn't look like there's anything that hits V2 of length 2 from V1. All right, from V1 to V3 of length 2, well, actually, look, you have this one, then you can go around that way, or you have this one, you can go around that way. There's 2. So there's 2 paths of length 2 that hit that one, okay? And then from V1 to, and you can think, okay, V1 to V4, length 2. Oh, look, actually, you have this one and that one, and that one and that one. That looks like there's 2. So this is only the top row of A squared. You have to keep on going to get more rows, but we can check to see if that's actually what we get as our top row. Simply here in this matrix, taking the top row of it and kind of inputting it as a row into this matrix and seeing what we get. So we input this row into this matrix, thinking of it as multiplication on the left, and think of a linear combination of the rows. So 0 times the first row, 2 times the next row, that would give you a 0, 0, 0, 2. Then you have 1 times the next row, and 1 times the next row, add them together. Actually, you do get that. So it really does work, all right? So you can get A squared either by actually directly matrix multiplying or even by looking at the digraph in that particular way. Now, let's just matrix multiply to get the next one. This is pretty simple. This is a linear combination of the rows right here. And it's just 0 down 1 times. That's just zeros. You can double check this is really going to give you A squared too as you go. Here, this is just going to pick out 2 times that guy right there. So it's just 2 times this row. So it's just a 4 there, a 0, 0, 0. And then here, that's just going to be another row of zeros. And let's double check ourselves here, maybe on this row here. What does this tell us? This tells us that there should be 4 paths of length 2 that go from V3 to itself. Let's see, V3, yeah, V3 to itself. Okay, let's see. You come out of V3. Let's see, from V3, I could go this way, and then on that arrow. Oh, that's one. Or I can go this way, and then that arrow again. That's another way. There were 2 ways starting with this loop. Okay, now what about the other loop? You can go this way, then that loop again, or you go this way, and then that guy. There's 4. Okay, that looks pretty clear. And notice there's no paths that come out of V3 to anything else. So that works perfectly. You can double check it and but everything else is just zeros. You can look at that to verify. Thanks for watching.